In the previous video, we looked at compounding annually. When it's compounding annually, n is 1 because you compound one time in a year. When it was compounding quarterly, n was 4 because we have 4 quarters in a year, right? Let's compound a little more frequently. What about compounding monthly? I wish my bank compound continuously. Compounding monthly, we use n equals 12. Okay, n is increasing, right? From annually, quarterly, monthly, and the last one, we were compounding what? Let me pick another color. Oh, green one. We were compounding daily. For daily, we use 365. So what if you compound continuously every moment? Okay, that's the case we call compounding continuously. But we can't plug in an infinity symbol here, right? So let's see what happened, okay? As n gets infinitely big, what will happen to the compounding interest formula, okay? And I prepared this little table for us to explore that, okay? What if n is 10, okay? What if we are compounding 10 times a year? Let's figure out what that number is. We have to do 1 plus n. Oh, okay. This piece, it came from the compounding interest formula, okay? Oh, I wish I can, should I talk about that? Okay, if I copy this real quick down there, I'll go ahead and duplicate this. All right, hold on. I want to talk about where that fraction came from, okay? Ignoring the principle, okay? We're just trying to come up with a formula that will work for any amount of principal that we invest, okay? So ignoring the principle, ignoring the time frame, okay? We're not even gonna, limit this to 5-year or 10-year, ignoring the number of years, so got rid of that t. And just ignoring the rate, okay? R could be anything. R could be anything. I'm just going to get rid of the R and put the 1 there, and that's where this fraction came from, okay? So only looking at the compounding period, the only variable of n, okay? What will happen if that n gets really big? That's what I want to explore with you in this video, okay? So let us see. If n is 10, the expression becomes 1 plus 1 over 10 to the 10th power. I'm going to go ahead and get the decimal approximation, but let me go ahead and just write all of these down first, and then we'll type in all of them all at the same time, okay? 1 over 100 raised to the 100th power. 1 plus 1 over 1,000, so we are compounding 1,000 times a year. And next one is what? 1 plus 1 over 10,000. Why are we doing this? It's because we can't plug in an infinity. That's why we're trying to see what these numbers are approaching, okay? That's why I'm just plugging in, these big numbers. All right, so I did set up everything. I'm going to go and find these values on a calculator, okay? Okay, let me get rid of some of these lines. All right, the first line was what? Whoopsie, let me bring it up a little bit. But the first line is 1 plus, parenthesis, 1 plus 1 over 10 raised to the 10th power. That number is 2.59374246. Next number, we'll copy this and change the denominator to 100. Change that exponent to 100. That number is 2.7048138229. All right, next line. Let's divide by 1,000 and raise it to the 1,000th power. Look at that. 2.716923. This is looking more and more like that one number that you may have seen before. All right, what's next? I'm going to add one more zero here, one more zero there. It is now 2.718145927. All right, last one. I'm almost done. Add another zero, add another zero. It comes out to be 2.718268237. Guess what? Do you see the pattern though? It's kind of getting close to what? 2.18 blah blah, right? So what is that number? I mean, you guys know what pi is, right? If I ask you, hey, what is pi? You're going to tell me pi is 3.14. Remember, there's another very popular irrational number in math that you may have seen before. That is e. As n gets infinitely big, this term that we were evaluating, this is getting closer and closer to e. So that's why in a compounding interest formula, we are going to have to use this natural base e. Okay, so here comes the formula for you. If you want to find the future value of an investment where interest is compounded continuously, you have to do the future value equals principal times e raised to the rate times time power, rate times the number of years. Okay, so this is the continuous exponential growth function. Okay, so let's go ahead and answer this question. So Luis, this time he still had $5,000, but this time he is investing what? At an annual rate of 3.25. Find the future value of Luis's account after 5 years. And here comes the keyword, you guys. If the interest is compounded continuously. If you see that, if you see the keyword compounded continuously, this is telling you to use that formula. Use A equals PERT. Okay, so let's plug in everything. E is just a number, but R is 0.0325 and T is 5. So if Luis can find a bank that will work with him on continuously compounding interest, then how much money will he have in 5 years? 5,000 times e raised to the 0.0325 times 5. He's gonna have $5,882.24. So that is the most money that he can get. Look, in that same investment period compared to this is 82.24, right? This is more than anything that we got from compounding annually, quarterly, monthly, or daily. Okay, so keyword is compounded continuously. Then you need to use this continuous exponential growth formula. Okay, don't think I've been going too far. So let me go ahead and talk about doubling time in this video too. So a very good question is, like, Luis is wondering, he got $5,000, but he wants to know when will his account double in value. So today he has $5,000, but if he put his money into an account, wait for it to grow, someday his money will double and become $10,000, right? So this is asking, when will Luis's account double in value? Remember, we're gonna go with can you go ahead and add this for me? We're going to assume continuous compounding. So remember, his equation was A equals 5,000 times e raised to the 0.0325 times t, right? Give me 1 second. Let me check the rate one more time. Yes, rate is good. But do you understand why I put t as a variable, right? Because it's asking for when will it So we're looking for how many years will it take for Luis to have $1,000. Oh, I'm sorry, $10,000. So I'm gonna go ahead and put down $10,000 on the left-hand side. And if you're wondering where did you get $10,000 from, that is his original money doubled. So 5,000 times 2 is 10,000. That's where I got this, okay? All right, we need to now solve this. To solve for t, go ahead and divide both sides by 5,000. First step, divide both sides by 5,000. 10,000 divided by 5,000 is 2. 2 equals e raised to the 0.0325t. Now, to get that t down, we're going to now take natural log of both sides. Okay, so take a look. I'm going to take natural log of 2, and I'm going to take natural log of that expression. The reason I did that is because if we take natural log, that exponent can come down, right? Remember one of that log property. So the left-hand side is still natural log of 2, but now the right-hand side is 0.0325t. And remember, natural log of e, that is just 1. So if it's just 1, I don't really have to write it, right? So I'm almost done solving for t. All I need to do is divide both sides by 0.0325. 0.0325. So we are about to find out how many years Luis needs to wait for his money to double and become $10,000. So t is approximately, I'm going to go ahead and type in this answer in the calculator so that we can get a decimal approximation, okay? So if I type that in, natural log of 2 divided by, natural log of 2 divided by 0.0325. That comes out to be, I'm sorry, Luis, he's going to have to wait 21 years and 3, I'll go ahead and say 21.3 years. I'll just go ahead and round it however I like. That many years he has to wait, even if it was compounding continuously. But here's the thing though, you do not have to solve equation like this every time you're looking for doubling time. There is a formula. It's always going to be natural log of 2 divided by rate. It's always going to be natural log of 2 divided by the rate, okay? If it's tripling time, you'll do natural log of 3. But theorem 4, we kind of just give you the exponential growth rate r, and the doubling time t is equal to this right here. So you can use this instead of solving equation every time. So this is the doubling time formula, and I will use that to solve this Facebook problem, okay? Facebook membership. Facebook connects people with other members they designate as friends. During its period of heaviest growth, membership in Facebook was doubling every 6 months. Oh, wow, okay. What was the exponential growth rate of Facebook membership as a percentage? Now, I was going to use this doubling time formula, but they already gave us that the doubling time is 6 months. Instead, they are asking for the exponential growth rate. They're looking for R. So guess what? I'm going to use this formula. All of these that we see are just the same exact equation solved for a different variable, okay? So the exponential rate is equal to natural log of 2 divided by doubling time t. Okay, now what is t though? Remember it said it doubled every 6 months, right? Now look at what I'm about to tell you. T is not 6, okay? T is not 6. T is 6 months, and that is half a year. You agree with me? Because we have 12 months in a year, 6 months is exactly half the year. So you must plug in t equals 0.5 in the denominator. Okay, so let's go ahead and find that decimal. All right, I'm going to go ahead and type this into my calculator. Natural log of 2 divided by 0.5. It comes out to be approximately 1.386. But remember, they wanted us to write this as a percentage. To write this as a percentage, I just need to multiply this by 100. Multiply by 100 to convert to percentage. Okay? So what was their growth rate? Or what was their exponential growth rate? That will be, I have just moved decimal 2 to the right. I will say it is 138.6%. And that is how you do this doubling time or exponential growth rate type of problems. These formulas are going to be useful. I think I'm going to put one problem on doubling time on your second test. So remember this formula. It will be pretty handy so that you don't have to solve equations like that every time. Okay, I'm going to stop this video here and come back and show you a couple more on exponential and log equations later.